which of the discrete messages had been sent through that system. And that process is called modulation and transmission. And that brings me to my second topic on that short outline that I showed to you earlier, modulation. So with that as a high level or kind of heuristic view of what modulation is, what we do in section 1.1 of the notes is we actually mathematically or formally define the process of modulation. Now this particular definition that we use in chapter 1 goes back to an approach that was used by MIT in the 1960s. Actually, there was a classic textbook by Wozencraft and Jacobs, and yes, Jacobs is Irwin Jacobs, who is now the CEO and chairman of Qualcomm, a big company that many of you have heard about, who really pioneered this particular approach to describing modulation. I parallel that approach from 40 years ago almost exactly in the first few sections of the notes, and then actually use it to develop other concepts which are different. That textbook is otherwise out of date, other than the basics that it has on modulation. So it's a very nice approach to this area. And this approach is pretty much used universally, I think, throughout the industry today in all the textbooks on how to describe modulation. In particular, it's what is called linear modulation, which is almost exclusively used. And in such modulation, we first describe something we call a data symbol value. And we give it a name x, and I put an underline under x to denote that means a vector, okay, of capital N components. So it's an n-dimensional vector. In the notes, I use boldface. It's really hard to do boldface on camera here, so I put an underline on camera when I'm talking about a vector, so you'll know that it's a vector. And that vector has n components, which we'll call x1, x2, through x sub n. And there will be a mapping from messages, which are indexed by some index I, to data symbols. So each message will be represented by some n-dimensional vector. N is going to be called the dimensionality of the modulator. Okay, but for now, it's just the number of elements in a vector. Each message has a vector associated with it. This mapping is called an encoder in digital communications. Take message bits in, produce a vector on the output. The components of the vector can be real numbers, any real numbers you like. We'll describe different sets later. Anytime we do that, that process is called an encoder. And the data symbol is one of two things that I need to formally describe modulation. The second thing that I need is what's called an orthonormal basis. Same capital N, and it's a set of functions. So I have n functions. I could write it this way with brackets, phi n of t, n equal 1 to capital N. And you'll notice I start the message index I going from 0 to capital M. For the modulating basis functions, I'm going to actually start the index n at 1 and go up to capital N. But there are capital N functions. And these functions, phi sub little n of t, have a nice property. And that is, if you integrate them over all time, any two of them, phi n of t and phi m of t, dt, you get a non-zero value only when m is equal to n, and that non-zero value is 1. We have a set of functions like that. It's called an orthonormal basis. Nice set of functions, and they're used along with the concept of a data symbol to describe a modulator. So what modulation is formally is the construction of the analog waveform. Remember, we decided a few minutes ago that we wanted to use 150 hertz plus or minus to get through that bandpass channel that we used as an example. More generally, we would like a set of waveforms like plus or minus cosine 150 hertz, but it may be for a different channel. And that set of transmit waveforms that represent each and every one of the capital M messages can be constructed in a linear modulator by taking a sum over all of the dimensions of the data symbol vector, which is for the ith message, and we'll have a component in the nth position in the vector, and multiplying by a corresponding function selected from the orthonormal basis. The orthonormal basis has nothing to do with the message set. The orthonormal basis are analog functions. They will be chosen or designed so that when they pass through a particular channel, they look different on the output, okay, so that they're distinguishable. The data symbol vectors otherwise are a function of the message set, and really not so much a function of the channel itself. So we're going to see that there are certain types of encodings, which are mappings from indices into vectors, which are good, universally good, no matter what the basis functions we use for the channel. So we're basically dividing this process of mapping messages into analog waveforms into two parts. Okay. Get some nice set of vectors that look kind of far apart. If I had that set of vectors at the channel output, it would be easy to resolve which of the messages were actually transmitted through the system. And then what I'm going to try to do is transport every component for any particular message along a basis function that hopefully passes very nicely through the channel and looks different. That's what this orthonormal basis means. Okay, they don't have a lot of commonality here. They look very different. Okay. Now hopefully they maintain that property at the output of the channel, but at least when they start going into the channel, they look pretty much different from one another. We may have different sets of orthonormal bases, and that will depend on a channel that's used. So we could think of the modulator basically taking components from some message. We'll have capital N of them. Though it's a data symbol value, there'll be one of these data symbols for each and every message. Once I have one of those messages to be transported, then I take the first component and I multiply it by the first basis function in the orthonormal set. And I take the second component and I multiply that by the second basis function in the orthonormal set. And what I will do is then, over all capital N dimensions of the modulator, I'll sum these weighted basis functions together, and I will produce the analog waveform that goes through the channel. And so that's modulation. That's construction of an analog waveform to try to get it to pass through some particular channel. Now for the example we saw earlier, it's pretty easy. I'd have maybe one orthonormal basis function would be cosine of 150 hertz. I'd have to normalize it so its amplitude is 1. I'd have a one-dimensional system, and the data symbol values would be plus or minus some number. We could say plus or minus 1. We want to transmit through the system. And we know that that basis function, 150 hertz, passed through the channel pretty nicely. Now, I might go back to that channel and say, why did I pick 150 hertz? I had from 100 hertz to 200 hertz. I might as well have picked maybe 125 hertz and 175 hertz. And I could have had two orthonormal basis functions. I'd have one in half the band, the other one in the other half of the band. Okay, and then I could construct messages knowing that I could send plus or minus either one of those, send them through, or I could maybe even send multiple amplitudes on each of those through the channel. And I could begin to construct different sizes of message sets that would pass through that channel. Now, this whole concept of the plus or minus and how many dimensions is summarized for the encoder in terms of what's called a signal constellation. A signal constellation is basically the set of vectors that correspond to the messages. So from I going from 0 up to capital M minus 1. Now we know that those get mapped into xi of t. Those are the modulated signals that are transported through an analog channel. The signal constellation itself is a set of M vectors. Okay, we're going to see some examples of that momentarily. We already saw one example where it would be plus or minus 1 for the 150 hertz transmission through the bandpass channel. One more definition, though, before I go to some examples, and that is data rate. The data rate of a communication system, sometimes referred to as R for rate, is defined as B, which we know is log base 2 of M, over some time period called capital T, where T, we can write this as log base 2 of M, the number of messages, T, where T is the so-called symbol period. Some people also refer to this as baud, but that term is so badly abused in communications, it's best to use symbol, very clear in the definition. So it's a number of seconds. If I had one bit, so 2 messages being transmitted, and I did that 10,000 times a second, my symbol period would be 100 microseconds, 1 over 10,000, because I'm transmitting a message every 100 microseconds. And the data rate would be 10 kilobits per second, or 10,000 bits per second. 1 bit times 1 over t, which would be 10,000, would be 10,000 bits per second. Lots of times I get questions, not from engineers like yourselves, well, maybe from some engineers, but from reporters who call me up and they say, some new transmission technique, I don't know where it came up in the world, but they're trying to raise money on Wall Street, and I get a phone call and they say, but the bandwidth of the channel is only, let's say, 1 megahertz. So how can they get 10 megabits per second through a channel with 1 megahertz? Doesn't work, right? Isn't there some kind of fundamental, violation of the laws of physics? No. We're talking about data rate, 10 megabits per second. If I had a message set every microsecond, let's say I had bandwidth of a channel around 1 megahertz, maybe might allow me to send a message every 1 microsecond. But I had 1,024 messages that I could select from, which would correspond to 10 bits. Then the data rate would be 10 divided by 1 microsecond, or 10 megabits per second. Bandwidth does not necessarily equal to the data rate. Clearly, it's related to bandwidth. More bandwidth, higher data rates. But another thing that's important is whether my receiver can resolve a lot of messages or not. And that's a function of basically how much signal energy I have and how much noise or how much distortion. So how many messages can I resolve? If I can resolve more than 2 messages, then my data rate can be higher than the bandwidth of the channel. So that's how that happens. So you don't want to confuse data rate with the bandwidth in Fourier transform terms of h of f to describe a channel. Happens all the time, unless you've taken a course like this one someplace, then you, of course, have seen this effect, but there is a difference. This is called the symbol period. Okay? Usually 1 over the symbol period. is roughly proportional to the analog bandwidth of a channel. Okay. We're going to see ways to go faster than that later as we proceed, but roughly order of magnitude, that's correct. And then we're going to be looking at how many messages are actually being transported through the system. Okay, let's look at some examples of modulation. Very simple example that we actually just designed a few minutes ago is called binary phase shift keying, or BPSK. We had two signals, plus or minus cosine of 150 hertz t, that we could send through a transmission system. Let's look a little different situation where, let's suppose we're looking at satellite TV. So for instance, DirecTV or Echo Star, perhaps you get that for your delivery. Typically what happens is you see a data rate of 40 megabits, that's what the M stands for here, per second, transmitted over a satellite channel. That may be more than one TV channel, okay? Maybe like 20 TV channels if we have 40 megabits per second. Somehow in my set-top box it's going to take the 40 megabits and chop out the 10 TV signals. But in terms of an aggregate transported signal through that system, it's 40 megabits per second. And the number of messages that are used in BPSK are two messages, and typically the number of dimensions is written as 2. And the two basis functions we see are phi 1 of t is equal to, I'm going to write it here, so I'm going to put a normalizing function out in front. I'm going to normalize to the symbol rate t, and let's just say plus pi over 4, some phase angle. And I have a second function, same normalizing factor, and cosine 2 pi t over t minus pi over 4. You'll notice here I've actually taken the two functions we talked about earlier. We had 150 hertz in here. 1 over t could be another number for a different channel like the satellite channel for transport. And in fact, in this case, t is going to be 1 over 40 times 10 to the 6th, which you work that out as 25 nanoseconds. So every 25 nanoseconds, one of two possible messages is transported from a satellite down to me, or from some kind of TV source generating up to the satellite. Typical frequencies that are used are on the order of 11 gigahertz to, I think the upstream things are around 18 gigahertz up to the satellites, and down they're in the 11 to 12 gigahertz range. But these are the types of modulation functions, because that's an analog channel. Okay, in fact, you got to get way up to 11 gigahertz or 18 gigahertz to be able to transport. And every 25 nanoseconds, either a plus or a minus, I think of as a message, is transported. Now these two basis functions, why did I write them in this kind of obtuse way? Well, I put the square root of 2 over t, you could actually integrate the square of one of these functions. You would see because of this 2 over t here, I get a cosine squared, and that integrates to have 1. Okay, so that's one of the conditions I need for orthonormal basis functions. And the other is that the two have to be, when I multiply one by the other and integrate over all time, that I get 0 for that. And that happens also with these two functions. Now, in this case, these are only going to be defined like this, so we kind of multiply them by a rectangular window over the symbol period. Okay, next symbol period, we restart the waveform. Now, these are orthonormal, and we can actually define a signal constellation for these two, which are two-dimensional vectors, 1, minus 1, and x1 is equal to minus 1, 1. And so if I were actually to plot these, let's call one dimension phi 1 and the other dimension phi 2, what I would have would be a couple of points that look like this. This is the signal constellation. They're basically diagonally opposite on a square. Now this would be a good constellation to use for two basis functions, no matter what those basis functions were. Because as you look at this, as long as they're orthogonal to one another, so they both kind of transport independently, as long as I don't have distortion in my channel. Got two things that look completely different. That's what the orthonormal part means. This data constellation, what it's doing is for a given amount of power, larger signals take more power. It's basically spread these two messages as far apart as you could possibly hope to get with two messages. Would be diagonally opposite one another, plus and minus. So any noise that might get added by the channel has really got to be a pretty good noise to throw me up here closer to this point to cause me to confuse which message was transmitted across the channel. I could do this for 40 megahertz, for 150 hertz, or I could do it for any other frequency. It would depend upon the band that I'm allowed to transmit through on my channel. It may be different for a satellite than it is for a cable modem or